Hello, everybody, and welcome to Understanding Virtualized Memory Performance Management. My name is Kit Colbert. I'm a principal engineer in the vCenter Operations Group at VMware. And speaking with me today is YP.
Yeah, good morning. My name is YP Chen. I'm with Kingston Technology. As most of you know, that's the memory company I hope so. I've been with Kingston for the last almost 6 years, primarily focusing on virtualization and security.
Okay, so I'll do the first part of the talk, and then YP will come up for the latter part. So, what is the agenda for today? Well, I wanted to start off and spend just a couple of moments on the motivation for the talk, why I'm doing it, what questions I hope to answer for you guys, what you'll get out of it. Then we'll delve into some concepts. In the end, what we want to do is monitor and manage and do best practices. But in order to do that, we need to have some intellectual framework, some understanding to know how to get the best out of monitoring and managing performance, and then what the best practices are for virtualized memory performance. So let's get to the motivation. So there's a number of concerns and questions that come up around memory performance, a number of different areas. One is the VM's configured memory size. Simply put, how big do you make it? Setting it too small will impact that VM's performance, but setting it too large will waste memory and possibly impact other VMs' performance on that same host. And then another question is, how do you size the host? How many VMs do you put on that host? Adding too many will impact the performance of the VMs on that host. But if you add too few, then you're not going to get the most use out of your host memory. So there's a common middle ground here that we want to try and find. And then finally, we have memory reclamation methods. There's a series of best practices around how to do it such that if memory needs to be reclaimed, we can do it in a performant manner, not affect the performance of those VMs. So what are the questions? I think I outlined most of these on the previous slide, but essentially, how much memory do you give your VMs? What data do you base that decision on? How can you justify that decision, especially to these application owners who always want more memory? How many VMs do you put on a host? How do you know when you have too many? How do you know that you need to scale it back? What do you do in that case? Do you always enable ballooning? Are there some cases where you don't? Does an SSD actually help with swap performance? And in the end, how do you monitor and manage all this stuff? So these are the types of questions that I hope I can help answer today. Okay, on to the concepts. So at a very high level, I wanted to go over some memory terminology. So we have the configured memory size. This is the total amount of memory that's presented to the guest operating system in a VM. Now, this memory size breaks down into two different things. We have allocated memory, which is memory that's been assigned to VM or to applications. And we have free memory, and that's memory that has not been assigned, or that is not currently assigned. Now, on the allocated side, that actually breaks down itself into two different categories, one of which is active memory, and that's allocated memory that has been recently used or accessed. And we have idle memory, and that's memory that has not been recently used or accessed. And we can do this more visually in a diagram. Here we have this bar graph. We see that the total length of it is the configured memory size of the VM. The allocated is some subset of that, with that breaking down into active and idle, and then free memory. So this is, again, a very high-level depiction. It's not necessarily meant to represent exactly what memory looks like in a real running system. It's not like all active memory is in one location. In reality, things are spread out. I've just done this here for simplicity. Now, another concept I want to talk about is that there are two levels of memory. The guest operating system thinks it's running on a physical host. It doesn't know it's in a VM. Thus, it believes it has physical RAM, and it's going to use that RAM, or that virtual RAM, however it feels that it can. But we know what's happening. We know the truth. And there actually is real physical RAM underlying that is managed by the hypervisor. The hypervisor makes decisions as to what to do with that RAM. It can give some of it to a VM, give some more to another VM, or to maybe take away some of the VM's memory and page share it, balloon it, compress it, etc. So there's two different levels of memory here. There's a top level that the VM sees, and that's what the VM manages. And then there's the bottom level, which is actual physical RAM, and that's what the hypervisor manages. So as I said, that top level is sized to the guest operating system. It's controlled by the guest OS. The bottom one is sized to the amount of physical RAM you have in your system, and it's controlled by the hypervisor. The hypervisor also manages the mappings between these two levels. So the hypervisor may choose to map some of that guest memory down to actual RAM, or it may choose to swap some of that memory out or balloon it. Now, the funny thing is that the guest has no idea that any of this is going on. It's completely transparent to the guest operating system. The hypervisor does this in order to protect VMs from one another, so they don't write on each other's memory, and also so that it can actually manage the memory very efficiently, make the best use out of it, so it can reclaim memory from VMs that aren't using it as actively and give it to VMs that are. So this is a really important concept to remember when you're thinking about how to do performance management. Now, let's get into a few terms here. So, terms that are relevant for performance. I like these two terms, demand and entitlement. Very simply put, demand is what a VM wants to use. Entitlement is what it gets, or is what it's allowed to get. Demand is based off of active. We saw active memory from a few slides ago in that breakdown. It may be greater than active, though, because the VM may be limited and not able to get all the memory it wants. And so demand is really saying what it wants. In a perfect world where there are no resource constraints and it could use as much memory as it wanted, what would it use? That's what demand is trying to measure. Entitlement is saying what it actually gets, what it can get. So you know that if what you want to use is more than what you can get, that's probably not a very good thing. And indeed, the drawing is trying to depict here that demand can be greater than, less than the amount that's mapped to physical RAM, as can entitlement. They both can vary independently of each other. But this concept of demand and entitlement and their relationship brings us to our first key concept around memory performance management. And that is that a VM will achieve its best performance when its entitlement is greater than or equal to its demand. Again, that means that the memory it wants to use will all fit into physical RAM and thus achieve the best performance. So what is this entitlement thing? Well, as I said, each VM has some amount of configured memory, let's say 4 gigabytes. But that's up in that top level, the VM level. At the bottom level, the hypervisor manages that. Each VM is entitled to some amount of memory of that physical RAM. It may not get its entire 4 gigabytes. It may get something less. Depends on a number of factors. It's essentially the entitlement is the VM's fair share of physical RAM. This is an important concept to know because this effectively says how much RAM this VM is getting access to and thus how fast it can run. Now, how is entitlement computed? Well, it looks at a number of different parameters, most of which you're probably familiar with. It uses the reservation. That sets the minimum bar for entitlement. It uses the limit and the configured memory size. Those two set the upper bound for the entitlement. It uses shares. That helps figure out where in the middle it falls. It also uses something called the idle memory tax. You may have heard of this. So the concept behind this actually is that we want the physical RAM of the host to be used by VMs that are actively using that memory. We don't want that memory to sit idle. This is physical RAM. We want to make the best use out of it. So if we have some VM, let's say a very large VM, like a 16 gigabyte VM, but it's only actively using maybe a gigabyte, we shouldn't be giving all 16 gigabytes to that VM if other VMs could actually use that memory. So we add a tax on idle memory. If the VM has a lot of it, then we'll bring down the amount of entitlement that we give that VM. In any case, all these factor into computing the end result, which is the entitlement. Now, let me do a very simple example of what this looks like. So we have 3 VMs running on this host. They add up in total to 10 gigabytes of configured memory, VM memory. But you notice the host only has 6 gigabytes of memory. This means that we can't satisfy all that VM requests, that some of that memory won't be in physical RAM. Now, if we take a look at VM 3, we see that its reservation is equal to its memory size. No limit, no idle memory. So its entitlement is 2 gigabytes, pretty simply. It's pretty simple, actually. So he gets 2 gigabytes. Now we have VM 1 and VM 2 left over. They're pretty much identical in that they have the same memory size, 4 gigabytes, no reservation, no limit, no idle memory. But the shares are different. In fact, VM1 has 3 times the shares of VM2. So since all else is equal, it comes down to the shares. Since it has 3 times the shares, it gets 3 times the memory. So in this case, the entitlement works out to 3 gigabytes for VM1 and 1 gigabyte for VM2. So this is a very, very simple case, but I wanted to try and illustrate how entitlement works and how you can have overcommitment here, but the host decides which VM gets access to that physical RAM. Okay, let's shift thinking here for just one moment. So we have these different methods of reclaiming memory. Transparent page sharing, ballooning, swapping, compression. I think you're familiar with all of them. And these are all great, but when are they actually used? And how much memory do we reclaim when we use them? Well, transparent page sharing is always running. It's always running. It's going to try and share whatever it can. But it may or may not help. It really depends on what's going on with the VM. How much shareable memory does that VM have? So let's put that one aside. So we have leftover ballooning, compression, swapping. So they're the only other way to reclaim memory. But each has a little bit of a cost. YP will go into this in a bit more detail later on in the talk. There's a bit of cost, a bit of overhead to running those. So we don't want to run them if we don't have to. We don't want to reclaim memory if we don't have to. So the question is, when do we have to? When do we need to do it? So there's one more term that I want to define here before we answer that question. And that is the notion of consumed memory. So consumed memory is the amount of physical RAM a VM has allocated to it. That's the consumed amount. Entitlement is very similar to consumed in that entitlement is the amount of memory the VM can get. Consumed is what it actually is using, which may be greater than or maybe less than the entitlement. So when do we reclaim memory? It's all based on entitlement, really. Entitlement is computed every few minutes. We figure out how much memory that VM should be getting. Then we reclaim based on entitlement together with consumed memory. Again, how much it's allowed to get versus how much it is actually using. If consumed is greater than entitlement, that means we need to reclaim memory. And specifically, we reclaim the difference between consumed and entitlement. So if that VM is over the limit, then that difference over the limit is what we take back. It's what the hypervisor takes back, and we'll do ballooning, compression, or swapping to get that memory back. So that leads us to our second key concept. Memory is reclaimed only when consumed is greater than entitlement. Now let's look at an example here. YP is going to have a lot more detail on this. This is a high-level example to hopefully drive the point home. So we have a few different stats we're looking at here. We're looking at active, we have a limit set, and then we're looking at consumed memory. Now, we can see that active stays pretty low. Our consumed is pretty flat, and obviously our limit is not changing. But over on the right-hand side, you see a workload spike happen. Active shoots up. That means that VM is doing a lot more. It needs a lot more memory resources. And look what happens. Active shoots up and goes way past the limit, past consumed. And you can see consumed sort of goes up a little bit to try and match it. But then look what happens. ESX pulls that memory back. You can see how active takes a nosedive. Consumed goes back down. Now the VM's not deterred. It wants to use as much memory as it can. It's got a workload spike going on. So it shoots back up, tries to use more active memory. And indeed, you can see how consumed goes back up to match that. But then ESX quickly notices and says, hey, this is not okay. You got to come back down. So you can see how the VM's sort of fighting for memory here, and that's going to have a performance impact. It can't do everything it wants to do. So the overall algorithm looks something like this. If consumed is greater than entitlement, then memory needs to be reclaimed. Generally, we prefer ballooning to do this, but if ballooning is not responsive or if we're really, really, really low on free memory, then we will go toward compression and swapping. Now, on the flip side of things, if consumed is actually less than entitlement, if a VM vMotion off the host or workloads have dropped or something where now this VM's entitlement has grown, we can actually give it back some memory. So if it has balloon memory, we can actually give it back the difference between entitlement and consumed and deflate that balloon. Okay, the last concept I want to introduce, memory overcommitment. Pretty simple. Essentially, it's you add up all the VM configured memory sizes, all the things from the top level. If that number is greater than the size of the bottom level, you're overcommitted. And what the implication is that you may run out of physical memory and you can't satisfy all these VM requests. In that case, you'll have to reclaim some memory. So let's put it all together. If you're not memory overcommitted, then all VMs will have their entitlement equal to their configuration size or the limit plus any overhead. And if there's no limit set, then entitlement actually just equals the configured memory size. The top level actually equals what's there at the bottom level. This means that there's no need to ever reclaim memory. If memory is overcommitted, then some VMs, by definition, will have an entitlement less than they're consumed. Assuming no limits are set, the host will start ballooning when we hit these, ballooning and swapping when we hit these thresholds. So that leads us to our third and final key concept, that assuming no limits are set, consumed is greater than entitlement only when memory is overcommitted. So remember the second key concept here was that consumed is greater than entitlement. Reclamation happens only when consumed is greater than entitlement. Now we know that consumed is greater than entitlement only when memory is overcommitted. Okay, so that was a quick jaunt through some of the concepts that will be underlying our discussions of monitoring and managing performance, and then the best practice section. Now, what stats should you look at to know how your VMs are performing? Well, there's a few new stats that we've introduced in 5.0, which I think really help in terms of doing performance management. They are memory entitlement and memory latency are the two new ones. Memory entitlement is exactly that. It's the amount of memory, that amount of physical RAM that VM is entitled to use. Unfortunately, we don't have a good active metric in Virtual Center yet. We do have it in VCOps. But for Virtual Center statistics, memory active is... I'm sorry, did I say active? I meant a good demand metric in VC. But active can substitute in, and so you use active to look at how hard this VM's working, how much memory does it actually want to use. And then there's latency. Latency measures how long the VM is blocked waiting to get access to swapped, ballooned, compressed memory. Essentially, it measures the impact on performance from reclamation. And the way to use these stats, the way I like to do it at least, is to look at memory latency. And if it's ever greater than 0, ideally it should be 0 most of the time. But if it's greater than 0, then you want to look at these other two stats. You take a look at active, and you say, is that greater than normal? If so, there's probably a workload spike going on for that VM. If entitlement is lower than normal, what does that mean? Well, it means that there's contention with other VMs. Maybe other VMs actually are having a workload spike, and there's not quite enough capacity on this host to satisfy memory requirements. So in both cases, you might want to increase the reservation of your VM or just do some load balancing. And indeed, DRS, if you're running it, should take care of this sort of situation. Another stat that I like to monitor are the virtual disk stats. And we can do this because we want to understand, is there any paging happening inside of the guest OS? Remember, there's two levels here. And paging can happen on either level. ESX can do it on the bottom physical RAM level, or the VM can do it itself inside of its level. And so to monitor that, what you can do is you can create a separate virtual disk and put the page file or the swap file for that guest operating system on that virtual disk and have it be the only thing there. That way, any reads or writes to that disk are by definition reads and writes to the page file. And thus, that'll allow you to know, is your guest paging internally or not? Because if it is, that's probably a problem. You may need to increase the VM memory size if there's just not enough memory for that application. Or you may want to increase the memory reservation as the internal paging may be a result of ballooning. So again, these are useful metrics to monitor. Now let's switch over to the host. The host is pretty much similar to the VM. We want to monitor active for the total amount of activity going on the host. We also want to monitor latency, which tells you how long VMs on the host on average are waiting for memory. It tells you if you have, in general, a population pressure problem on that host. And then the other one is reserve capacity. And this is an interesting one. So you want to, I'm a big proponent of reservations, and we'll talk about it more in best practices. But you don't want to reserve too much. You don't want to reserve 100% of the memory on a host. The reason for this is that the VM, the VMM, the monitor that actually runs the guest operating system, it'll do different little tweaks. It maybe needs a little bit more memory to get a bit better performance, and so it'll do these things a little bit dynamically. So if you completely overcommit or completely commit out the reservations, then it's not able to make those slight adjustments for performance. So it's always good to leave a little bit of breathing room in your reservations. Maybe take it up to 90% of the host memory rather than 100%. Now, there are a number of options you can use to monitor performance. I've listed out the VMware ones. There are many other vendors besides VMware. So there's always the Virtual Center Performance tab. I think we all know that. It's very basic. As you know, it's not really a fully featured performance management solution, but it's useful for just seeing basic stats and for looking at some of that data. ESX Top is another tool you can use. It's really, really good for deep debugging. You can really get in there into the nitty-gritty. But it's generally most useful when you know that you have a problem. It's not very useful for monitoring, for asking the question, do I have a problem, and where? So that's why we have vCenter Operations, which again is the product I work on. And we've optimized that both for monitoring and for troubleshooting, to be able to look out at your entire environment, thousands of VMs, millions of metrics that are being collected, and tell you, do you have a problem? If so, where it is, who's affected, and what's the root cause? So there's some related talks I've listed here in case you're interested in more information. Okay. Now to the best practices. So for best practices, I want to break it down into two things. Separate out VM best practices from host best practices. So we'll start with the VM. Now, what do you want to do for VM? How are you going to size this VM's memory? So what you want to do for the VM is you want to guard against what I call active memory reclamation. And if that active memory reclamation is necessary, you want to make it as efficient as possible. So how do you do number one? Well, what you want is at the OS level, again, there's two different levels, and you can get reclamation at both levels, as I mentioned. The guest can swap internally, and the hypervisor can swap. So you want to make sure that the VM's configured memory size is large enough. If the VM needs more memory than it has, it's going to internally page, and there's nothing that the hypervisor can do about it. So you want to make sure that's set large enough. And what you can do is you can look at demand, look at the active metric, see what that is, trend that over time, and then make sure that the VM's memory size is larger than that, a little bit of buffers, so give it some breathing room. That way you can hopefully help prevent that internal swapping from occurring. Generally, this is not a problem from talking to most customers. Most customers, the application admins always want a giant VM, so your problem really is making it the right size, smaller, rather than needing to make it bigger. But nevertheless, it's something to keep in mind. On the hypervisor side, again, we go back to our key concepts. Hypervisor will reclaim memory if consumed is greater than entitlement. And that for best performance, we want to make entitlement greater than demand. And we know that memory reservation sets the lower bound for entitlement. Thus, if we make our reservation greater than our demand, then our entitlement will be greater than our demand. So we look at demand, we look at active, trend that over time, and you can then set the reservation based on that. So again, my product, vCenter Operations, actually is really good at doing tracking of data. It understands data, looks at it over time, develops normal baselines. So it's one way of understanding what the average behavior is for this VM. Now, we do those best practices. You set your reservation correctly. You size your VM memory correctly based on active memory, based on that demand. But nevertheless, you may have workload spikes. You may have things that happen, hosts fail. You've got to vMotion these VMs over. So if reclamation is necessary, how can we make it as efficient as possible? First, question of ballooning versus swapping. Perennial discussion, lots of arguments about it. In general, ballooning is the right way to go. Now, look at this data here. So on the x-axis is the amount of reclaimed memory. So it starts off at 0, meaning the VM gets its full 4 gigabytes. As you go further right, the value gets larger and larger. On the y-axis is the normalized throughput of this application. You want it to stay near 1. This particular application is a swing bench application. It's a database workload generator. The blue line is showing what happens if you have ballooning on only, and the pink line is showing what happens if you have swapping only. So you can see a pretty marked drop in performance on the swapping side. It's actually surprising how well ballooning does. It stays pretty close to 1 almost throughout. So what does this tell us? It tells us that for memory reclamation, ballooning generally outperforms swapping. And this is just one example, but it's proven across many different workloads that ballooning is very, very preferential. So how do you make sure you're doing your ballooning best practices? You want to install VMware tools on all your VMs. Hopefully you do that already. You want to enable ballooning on all your VMs. It doesn't matter what the workload is. It doesn't matter if the vendor tells you that ballooning is bad. You want to enable ballooning. A couple of things people trip up on is that they don't necessarily provide sufficient swap space inside the guest. You just need to make sure that there's enough space there for the guest to page out memory if it needs to. And it's easy to forget when you change the VM memory size that you probably want to change the guest swap space size as well. And as I've mentioned in the monitor and manage section, you can use the virtual disk stats to actually monitor how much guest swapping is going on if you place that swap file on a separate virtual disk. Okay, now let's do something. Let's take this graph out further right and see what happens as we start reclaiming more and more and more memory. So this is really interesting. We see that swapping, sort of just continues going off into the weeds here. It's done. But look what happens with ballooning. Look at that nosedive that it takes. What do you think happens here? Why are we getting that sudden nosedive? Well, as it turns out, it's right around, 2 gigabytes, give or take, that it starts, maybe even 1.8 gigabytes, that it starts going downhill. And why is that? It turns out we're actually eating into the active working set of SwingBench. SwingBench happened to use about 2.2 gigs of memory actively. And as ballooning starts eating into that, you see a huge drop in performance. So the takeaway is that, and I've been saying this overall, and this is in fact our first key concept, was that you have to ensure that the active memory, that the demand stays within physical RAM. And you can do that by making sure the entitlement is greater than the demand. Again, the entitlement is how much physical RAM that VM is entitled for, demands what it wants to use. You can see what happens when the demand no longer fits within physical RAM. We have to start ballooning it. You get a lot of overhead. You get a lot more latency. If you're watching the mem.latency stat, you see it spike up here. So make sure entitlement is greater than demand for best performance. Okay, so that's the VM. Now what about the host? Well, there's two things you want to do with the host. You want to add as many VMs as possible. This makes the best utilization out of your RAM. But you don't want to impact VM performance, right? It's finding that happy middle ground where you're optimizing the use of your memory, but you're not impacting performance of any of your VMs. So how can we do that? Okay, so I want to tease apart this concept of memory overcommitment. A lot of people, when I talk to them, they have this concept that overcommitment is just bad, that you shouldn't overcommit, that it's bad for performance, that it's just a bad thing, we stay away from it. That's not actually true. Memory overcommitment is actually fine, assuming you're doing the right type of overcommitment. And I distinguish two types here. The first is what I call configured memory overcommitment. It is when the total amount of configured VM memory that's powered on that host is greater than the amount of host RAM. And that's the same definition we had from a few slides back in the concept section. But there's also another concept of overcommitment, and that's overcommitting the active working set. So it's the sum of the VM's demand, or the active, divided by the amount of physical RAM. Now, what are the differences between these two? They're actually quite stark. Because if you just overcommit the configured memory, there's basically no performance impact. You might get occasionally some ballooning and swapping, but it's not going to hit the active working set of that VM, and thus it'll maintain its performance. But if active memory overcommitment is pushed too high, somewhere close to 100%, then you're almost guaranteed to have a performance problem. Again, if you go back to that SwingBench chart I showed you, you can see that at that point we were overcommitting the active memory, and you saw that nosedive. So it's a happy middle ground between maximizing the top one and staying conservative on the bottom one. So let me dig into these concepts a little bit more. So remember, one of the first slides, active, idle, and free. I've drawn them again here. So if we look at this, we see that in configured memory overcommitment, parts of the idle and free memory are not in physical RAM because they've been reclaimed. But we notice that all of the active memory in those VMs stays in physical RAM, thus giving you maximum performance. Again, you want to make sure that active memory stays in physical RAM. And when you overcommit the configured memory, that happens. So again, configured memory overcommitment is not a bad thing. It's not going to impact performance. It's actually a good thing because you're making optimal use of your RAM. Most of the RAM there is being used actively by these VMs, and that's a good thing. That's what you want. Okay, now let's look at active memory overcommitment. What happens here? Well, what we see here is that no idle or free memory is in physical RAM anymore. We just don't have the space for it. But what happens is that even some of the active memory doesn't fit into physical RAM. So what you see here is that place out there, that piece of memory out there is active, but it's not in physical RAM, so what happens? Well, the VM's going to try and use it because it's active, so it needs to swap that memory back in, so the VM's going to wait for that. It's going to start using it, but now the VM is over its entitlement. So now the host has to swap out some more RAM, so the other RAM gets swapped out, but the other RAM's also active, so that VM needs that RAM again, or that memory again in just a second, so then ESX has to go and swap that one in. And so you can see how you get this thrashing situation where you're constantly trying to access swapped memory or ballooned memory, and thus that nosedive that we saw in the swing bench case. So active memory overcommitment is something that you don't want to do, something you want to stay away from. So again, configured overcommitment, memory overcommitment greater than 1 is a good thing. Active memory overcommitment less than 1. Where you fall on the less than 1 scale is totally up to you. I always suggest 70%. Some people want to stay more conservative at 40% or 50%. Right now, I bet you if you look at this number on your systems, it's probably averaging 10% or less, I would guess, for most customers. But you can do a lot more with that memory. Now, we're on to the second part, which is to not impact VM performance. And for this, I'll hand it over to YP.
Okay, next I will title the concept that we just, hopefully you learned by using some examples that based on the memory test we just did under vSphere 5. So what we're trying to do here is, for the test is we will first inject some memory workload using in-house developed workload generators on a EXS server. In this case, have only 7.5 gig of memory. As you can see, there's a big deficit here, around 2 to 3 gigabytes of memory. So obviously, we can now force the EXS server into to do memory reclamation using ballooning, compression, or swapping. Okay, just give you a little bit idea that we'll run this test on a HP server with 32 gig of memory, and underneath that, we deployed 12 Windows 2003 VMs with 4 gig of memory. So we have about 60% of so-called configured memory overcommit. And then when we inject additional load on top of that, now we really get this system into so-called active memory overcommits. Now we can study the memory reclamation techniques, and also we can look at the memory performance impact caused by those techniques. So you can see that when the memory drops, that balloon starts, and then certainly the swapping. Okay, so with that said, let's also see the here is the kernel state. So the kernel state goes from 0 is really high state, and 1 is, in this case, is low state. And we collect all the stats using EXS top in batch mode on a 6-second interval. So we collect about 30 minutes, so about 300 samples. Okay, so now we want to look at the memory reclamation in actions, and to show you how this EXX knows when to reclaim memory and from which VMs. Okay, we know that from the basic concept, memory reclamation is based on what? Entitlement and consumed memory. And also we know that entitlement is pretty much influenced by the amount of memory activity. It's just to see how active the VM is accessing the memory. If not, if we have a lot of idle memory, of course, when EXA needs to reclaim memory, this VM will be a primary target for memory reclamation. Okay, so let's take a look at the memory activity. In this case, this is the consumed memory, and let's plot the entitlement. Okay, so as Kit pointed out that when you have memory overcommit, what happens? Entitlement is less than consumed. Okay, so let's take a look at how EXS is going to reclaim memory under this kind of situation. So as you can see that when the entitlement drops, what happened? EXS starts to claim memory using balloons, right? And as the memory demand continues, EXS is going to continue reclaim memory from the VM using ballooning. Okay, let's see. At this point, the balloons pretty much top out at around 2.6 gig of memory. Okay, remember this VM has 4 gig of memory configured. And why does the balloon memory top out? Okay, I'll give you about 5 seconds to think, and before I give you the answer. Okay, think about it. Okay, so now I believe you already know what it is, so I'll give you the answer. By default, EXS will only balloon to the 65% of your configured memory. So if you have a 4 gig of memory, your balloon top out at what? 2.6 gig of memory, which is 65% of your configured memory. Okay, so this is what we're seeing here. Now what? If EXS need more memory, what happens? He's going to resort to compress or swap. So let's take a look at that. Okay, so now we see that the swap occurs. Okay, now we want to see why this VM is picked for memory reclamation. Of course, as I mentioned before, the entitlement is pretty much influenced by what? Memory activity. So let's take a look at the memory activity. So as you can see that at the very beginning of the test, this VM is pretty much idle. So of course, when EXS needs memory, where does he going to get it from? From the VM that doesn't need the memory. That makes sense, right? So you can see that the VM is picked to be the one to reclaim memory. Okay, so as the memory demand drops, I don't know, I'll show you that at around the sample interval of around 140, and this memory activity picks up. Now see what happens when it starts to access the memory, the swap in, and so the swap size reduces, and finally when it peaks out, the balloon deflates. So hopefully that makes a lot of sense to you. Okay? All right. Now let's take a look at the memory reclamation performance impact. Okay, as Kit mentioned that to measure the performance impact, we'll use memory latency. And since we're using the EXS top memory stats is called memory latency, percent of memory latency. So basically the same idea as the one that Kit pointed out. It's the percent of time the VM has not scheduled due to memory resource issues. Okay, so now let's look at the memory performance impact caused by swap. Okay, my question to you is, what part of the swap operation that has the most detrimental effect on the VM? Is that a swap out or swap in? Again, I'll give you about 5 seconds to try to answer that. Okay? So you already have the answer, I hope. So now let's take a look at it. So as you can see that most of the performance impact is caused by swapping in. Why? Because when swap out is totally transparent to the VM, and VM doesn't really need the memory, okay, at that time. Now, when the VM really needs the memory where it's on the disk, what happens? He has to read it back. And when it reads back, the latency is so huge because the disk is so slow. Later on, we'll show you how we can reduce that by using SSD. So as you can see that, in this case, boy, majority of the time, this thing is totally useless. So it's like 90% of the time. So let's try not to swap, okay? Buy more memory. All right. Okay. Even I say buy more memory, there's still a cache. I will show it to you. Okay. So here we turn on the compression. As you can see now, once we use the compression, everything is done in memory, and you can see that the big performance impact reduced. So now we're talking about 4%. Okay, and the amount of swap has become much lower. Again, I have to warn you, this test is based on what is our artificial generated workload. So what you see here may not be actually be the case in your actual environment. Okay, so this is just for your reference only. All right, so this all look good, but the question is, what could be the catch or performance impact of compression? Again, I'll give you about 5 seconds to think about, okay? So let's take a look at the performance impact caused by memory compression. So what do you think? Well, compression takes CPU time, right? That's obvious. So your CPU will be affected. So if you have a high CPU utilization here, then that will be your cost. So you have to really remember, even memory compression help you reduce this latency. You probably ship your problem from one place to the other. Okay, so I would like you to know that. All right, now there's another possibility that you may impact your VM's performance. Okay, so what that could be? So you may have paging inside your VM. Okay, so that's another thing you need to look at. Okay, I don't know if you know that the window performance stats can actually include the VM's memory stats. If you have you have the VM2 installed, okay? I don't know how many people know that. So actually, in our case, we also look at the performance and also look at ES at top, okay? Oh, by the way, that if you want to know more details about how we did all tests and what tools that we use, you can look at the white paper and also the blog posts that I listed in the reference section at the end of the presentation. Okay. Oh, now let's see how we can use SSD to reduce the impact caused by hard drive. Okay. Now we know that if we had to swap to disk because of the big performance difference, there would be a great biggest performance impact, as you already seen. And with SSD, we all know SSD is much faster and doesn't have the latency like the hard drive. So people now start thinking using SSD to improve performance. I just want to see how many of you that are thinking of using SSD in your environment. Please show your hand. Okay, so I will encourage you to really take a look at using SSD in your environment, actually not only for this case, and also if you go on the show floor, you see a lot of storage vendors now using SSD to improve performance. Okay, in vSphere 5 now, there is a new feature called swap to disk or host cache features. Okay, basically, the idea is to use SSD as a host cache to reduce latency caused by disk swap. And the nice thing is it's transparent to swap file locations and efficient use of SSD storage space. Just imagine that if you use SSD as your swap file and you have 10 VMs with 4 gig of memory, how much swap space you need? 40 gig, that's a lot, right? If you know you only need about, hopefully, less than 2 gig of swap. So you really don't want to use the SSD as a disk. You want to use that as a cache. Okay. So let's see how we use that. So in vSphere 5, there's something called auto tagging, and if you plug in SSD that can be recognized, you will show that as a SSD, or you can use a script to enable that. All right. And then on the vCenter, you can use host cache configuration to enable it. Okay, once this is enabled, now let's take a look at the performance impact reduction. So this is the thing you have seen, and then we run the same test. You see the big performance impact reduction. By the way, the SSD we use a very low cost one. So if you happen to use a high performance one, this may even look better. Okay, now let's talk about memory sizing, memory configuration. And the thing is, memory, even though I asked you to buy more memory, but you better know that memory, there are 3 speeds it can run on. And the actual speed, the memory actually run your environment now is depending on, 1 is the processor you're running on, 2 is the module speed, module that you buy. You buy an expensive one, you can probably run at 1333. Of course, you always want to run it at a higher speed, right? Okay. Also, the memory density called memory rank. So if you have a bigger capacity of the memory chip, you may talk about dual rank or quad rank. Okay. And then memory voltage and the amount of memory that you put in. So here is a trade-off now. The more memory you put it in, the speed may drop. Okay, so sometimes not necessary you want to put more memory. But of course, we'll encourage you to put more memory. So you see the trade-off now, okay? So you really need to understand that. Okay, now the final thing is if you plug in a memory ROM, and each server manufacturer has its own thing called population order. So I just want to run it quickly to show you this population order is non-trivial. Okay, I don't know how many of you have actually opened a server and add memory. Please raise your hand. Oh, a lot. Okay, great. So you probably should know, in this case, the HP, that where you should plug in the memory module. So if you don't know, it doesn't matter. But just to let you know, there's something you need to really be aware of. And actually, it happened to us, even we're a memory company. And one day, I opened up my server box, I find out the memory was configured wrong. Okay, so even happened to me. All right, so this is something that you definitely want to be made aware of. Now, your question is, how do I know my memory configuration is correct? Should I open the box, turn the power off? No, nobody. Your admin won't let you do that, right? Okay, so actually, you don't. Before I do that, I will just show you that the capacity versus memory speed. Okay, so as you can see that if you put more memory, in this case using 16 gig memory module, you can go all the way to 122 gig of memory, but now you run at 800 megahertz. Okay, so now, how do you know your memory are populated correctly? You go to the vCenter and take a look at it. Okay, so this is one place that you can take a look at. Then you will argue that I got 100 EXS servers there. I'm not going to spend so much time to look at it. Great. We wrote a script. Just copy that out. Okay. I'm a guy that's pretty lazy. Okay, so and my guy at tech support loved me now because I show them this and they say, oh, great. So I just tell the customer, run the script, you know what happens. Okay, that's all I have to say. Thanks.
Let's do a quick summary and then we'll open it up for Q&A. So going back to the concepts way back at the beginning of our talk, a VM will achieve its best performance when its entitlement is greater than its demand. Entitlement is the fair share that VM gets of physical RAM. Demand is how much it wants to use. Memory is reclaimed only when consumed is greater than entitlement, and assuming no limits are set, consumed is greater than entitlement only when memory is overcommitted. So we have the list of stats here that you want to look at: entitlement, active, latency, the virtual disk stats. And then in terms of the best practices, you want to guard against active memory reclamation by sizing the VM properly, making sure its configured memory size is large enough, and then using memory reservations. As I said, I'm a big fan of reservations. I think that if they're set properly, then you can ensure performance while overcommitting. You also want to make reclamation efficient, install VMware tools, enable ballooning, provide sufficient swap space inside the guest. And then on the host side, you can add on as many VMs as possible to keep configured memory size greater than 1, but to keep active memory overcommitment less than 1. And again, VM memory reservations are the way to go, in my opinion. For YP section, you don't want to impact VM performance. So we saw how efficient memory compression was. We saw how efficient using an SSD as a host cache was and reducing the performance cost of reclamation. So the idea with these two things is that they allow you to be a little bit more aggressive and to push overcommitment a little bit higher because the penalty for reclamation isn't nearly as large as it is with a normal spinning disk. And then, of course, as YP was mentioning, you got to make sure you know how to place your DIMMs and think about the trade-offs between adding more memory and then the speed of that memory. And then here's some references that YP was mentioning. I'll leave this slide up. And I think that's it for us. Thank you. So I will say, before we do Q&A, as you're walking out, please do fill out the surveys. The surveys are great, both for VMworld in general and for ourselves as speakers. You know, what do you like about us? What do you hate about us? So yeah, please take the time to fill those out. And then if you have questions, we have 2 microphones here. So if you don't mind stepping up to the microphone. Any questions? Okay. I'll repeat it.
vCenter shared memory shows up in the graph?
Yeah.